So in this video, we're going to hit the high points of sections 7 through 13 in chapter 15. And we're starting with the stereochemistry of radical reactions. And just like in any stereochemical description that we've had, we need to differentiate between the starting material being achiral versus chiral. And this table here is nothing new. And so especially this first row, where if you start with an achiral starting material, you're not going to get chiral products. You may get a racemic mixture, but you're not going to have a chiral product. As far as the chirality, it depends on where the reaction's happening, whether it's happening at a chiral center or it's not, or it's happening at another carbon, and we'll see those things. And so if we have an achiral starting material like butane, and we react it with chlorine, we halogenate it, we can get different regioisomers, the 1-chlorobutane and 2-chlorobutane. This is creating a chiral center, but you're going to get equal amounts of these enantiomers. And so it's going to be 1-chlorobutane's achiral, and you'll also have a racemic mixture in 2-chlorobutane. And the key really is this intermediate. The planar radical is going to allow equal attack from the back and the front to create a racemic mixture. And so again, if you've got achiral starting materials, you're either going to get achiral or racemic mixture. As far as if you are starting with something that's chiral, there are two places that things can happen. One being a chiral center. And if you have a chiral center like this in R2-bromobutane, and we have a reaction, we're going to create racemization. Again, planar achiral radical is the key, because we've now lost the stereochemical relationship, and you can get equal attack. And so you're going to have racemization take place if things are taking place at the chiral center. If we look to another carbon, if we look to carbon 3 in this case, what we're going to create is a mixture of diastereomers, because we're going to get racemization. We're creating a chiral center, but it's going to be racemic, and therefore we're going to have a mixture of two diastereomers in this case. And so that's kind of the keys to stereochemistry of radical reactions. In terms of the allylic carbon, something that we discuss is this resonance that can take place. And again, allylic means next to a double bond. So if you form a radical that's next to a double bond, it is going to be more stable than a tertiary radical, and that is because of resonance. And you can see here the reason why this is ultra stable is because we can now spread this out and delocalize the radical. And so therefore, this is a very stable intermediate. Now, in terms of a reagent that we can use for this, we can use NBS, which is N-bromosuccinimide, which is shown over here on the right. And it has a weak nitrogen-bromine bond that can allow a radical to form very easily, and we can get selective bromination of the allylic carbon, because these two carbons here that are not allylic are not going to form radicals nearly as stable as the allylic carbon. And so as far as how this takes place and how the reaction takes place, again, the weak nitrogen-bromine bond breaks with light, and then the bromine abstracts a hydrogen. The carbon-based radical can react with bromine. Now, this molecular bromine is formed at a very low concentration from the NBS. And so it can then react to create product, as well as, again, this is propagation, so we're getting another bromine radical. And this causes us to do two different things. If we add bromine, we're just going to get addition, which is going to be an electrophilic addition mechanism. Whereas if we use NBS and peroxides or light, we're going to get substitution. So it's a difference between addition and substitution. In terms of regioselectivity of the allylic halogenation. If you've got a choice, again, you've got resonance that is forming in the intermediate. And if you have resonance in the intermediate, you can get regio isomers. So we've got constitutional isomers showing up here, both addition products, or excuse me, substitution products, but we're getting different substitution products because the intermediate radical has resonance. The last, or one other reaction that we're discussing is the addition to alkenes. Now you might say, well, we know about addition. We did addition back when we were talking about addition reactions. Well, there's a little bit of a difference here. So if we look at this reaction on the bottom, and I'm going to have to go back, we can see this is no different from what we've seen, the addition of HBr to an alkene. But again, we're using different reagents. We're using peroxides and or heat and light. And what we get two different constitutional isomers forming. If we just use HBr like we had in organic 1, we get the Markovnikov product. But in this case, we get the anti-Markovnikov product, and that is because the more stable radical is forming. Okay? And just like the more stable carbocation forms in the regular addition, when we're doing a radical mechanism, the more stable radical is going to form. And so, again, this primary radical is not going to form because it's not as preferred, and that's why we only get this product. But if we're doing the ionic addition, which is down here, the more stable carbocation forms, and the hydrogen adds first in this case. In the radical addition, the bromine adds first. And so there are some similarities, but again, the regioselectivity is going to be different. Now, the final thing I'm going to talk about in this is polymerization. And this is really, we're just adding radicals to alkenes, and then they continue to add. And so these monomers that are referred to as monomers, the simplest units, these things continue to add and make longer and longer chains. And this is done by a radical mechanism. And you can have different, that was just ethylene, but you can have different things on the edge, and you can continue to make all different sorts of chains. Here are some examples of things that are used in medical, the medical profession or dentistry. We use Teflon actually in this nice glide floss. PVC and polypropylene can also be used in different packaging and syringes. In terms of how this takes place, you can see a lot of similarities here. We break a peroxide bond. This then creates the initial monomer, and that is the initiation. Propagation is the continual addition. And again, you can have termination if multiple chains come together. Okay, but this can continue. This process, this propagation process, can go on and on for multiple, lots and lots of rounds to make very long chains. And so, as you know, this is important in terms of the more substituted radical always adds to the less substituted end, because if this didn't happen, we would have lots of different types of polymers. And so this is just mainly a summary of the different types of reactions that we can do with radicals. And this concludes our discussion of Chapter 15.